NASA is developing a groundbreaking propulsion technology that could make interstellar travel a reality, cutting the journey to Alpha Centauri down to just 40 years. For now, space remains an enormous challenge due to its vast distances. But with the upcoming Sunbeam propulsion system, a research probe could one day travel at 10% the speed of light, reaching destinations once thought to be out of reach. So how does this futuristic tech work? What innovations could finally shrink the seemingly endless cosmos? And could visiting distant stars and exoplanets soon become more than science fiction? Stick around to discover the bold NASA concept that could revolutionize space exploration as we know it. Adding to the excitement, the James Webb Space Telescope has recently detected dimethyl sulfide in the atmosphere of exoplanet K2-18b compound produced only by life on Earth. This discovery stands as the strongest indication yet of life beyond our planet. Some scientists believe the oceans of this distant water world might even be filled with alien organisms. Just imagine launching a research probe to K2-18b, capable of confirming extraterrestrial life, and maybe even sending back images of it. The fascinating exoplanet K2-18b lies just 124 light-years from Earth. In the vast scale of the universe, that's practically next door, but for human space travel, it remains a daunting, nearly unreachable distance. To understand why, consider that a single light-year equals about 9.46 trillion kilometers. Despite nearly 50 years of continuous flight, NASA's Voyager probes haven't even traveled one light day. And it's not because they're slow, they're zipping through space at roughly 61,500 kilometers per hour. But even that impressive speed falls dramatically short when it comes to reaching other star systems. And K2-18b isn't the only world of interest. Astronomers have identified several potentially habitable exoplanets close to us, cosmically speaking. One of the most intriguing is Proxima b, discovered in August 2016. It's located just 4.2 light-years away in the Centaurus constellation and orbits the red dwarf Proxima Centauri. This star, in turn, is part of the Alpha Centauri system, a triple-star arrangement that makes Proxima b the nearest known exoplanet that could potentially host life. Proxima b, being the closest known exoplanet to Earth, naturally stands out as the prime candidate for humanity's first interstellar mission. But with today's technology, the harsh reality is that it would take a staggering 70,000 to 80,000 years for a probe to reach it. Fortunately, this timeline may be slashed dramatically in the future thanks to groundbreaking advances in propulsion systems that could finally turn interstellar travel from fantasy into reality. One such innovation is NASA's Sunbeam propulsion system. To understand the leap it promises, consider the current record holder for speed, the Parker Solar Probe. It has reached an astounding 692,000 kilometers per hour, making it the fastest object ever built by humans. Yet even this is a crawl compared to what's needed. NASA's Sunbeam concept is aiming far higher, a target speed of 100 million kilometers per hour, or about 30,000 kilometers per second. That's roughly 10% of the speed of light, a pace once confined to the realm of science fiction, now envisioned as a serious scientific goal. In this revolutionary vision, the journey to the Alpha Centauri system, once requiring tens of thousands of years, could be reduced to just 40 years. But how could that possibly be achieved? Surprisingly, the core idea behind NASA's Sunbeam propulsion system is quite simple. Rather than launching a space probe loaded with fuel, the probe would receive a continuous energy supply from an external source throughout its mission. This external energy source acts like a cosmic fueling station, delivering power via a focused particle beam. And this isn't about sending a lightweight test object. The goal is to launch a fully equipped 1,000-kilogram research probe carrying advanced instruments for deep space exploration. At the center of this propulsion breakthrough is the relativistic electron beam, a stream of electrons accelerated to nearly the speed of light. This high-speed beam delivers the necessary thrust to the spacecraft, pushing it steadily across interstellar distances. The beam itself would be emitted from a solar platform, known as a solar-stated, positioned close to the Sun. This platform would remain in place, stabilized by solar radiation pressure and magnetic fields, and would continuously direct the high-energy beam at the probe, acting as a remote engine driving it through space. The solar-stated plays a crucial role in this visionary propulsion system. It continuously delivers momentum to the spacecraft, allowing it to accelerate without using onboard fuel. The longer the particle beam is active, the faster the probe becomes. But this raises an important question. Won't the electrons in the beam eventually scatter across space? After all, electrons naturally repel one another due to their like charges. Thankfully, physics offers a solution: the pinch effect. This phenomenon, closely linked to Einstein's theory of time dilation, helps keep the beam focused. In simple terms, time dilation means that time slows down for objects moving near the speed of light, as observed from a stationary frame of reference. A common analogy is that a fast-moving clock appears to tick more slowly than one at rest. In the context of the Sunbeam drive, this time, dilation stabilizes the relativistic electron beam. The particles don't spread out as they normally would because, in their ultra-fast frame of reference, the repelling forces act differently. This keeps the beam tight and effective, even over immense interstellar distances. Why this matters? If this cutting-edge concept becomes a reality, it would be a game-changer for space exploration. For the first time, we could explore distant star systems like Proxima b within a human lifetime, not millennia. Proxima b, although likely tidally locked, meaning it has a permanent day side, and night side still lies within its star's habitable zone, making it a compelling candidate in the search for life beyond Earth. The habitable zone, often called the Goldilocks zone, defines the orbital region around a star where conditions are just right for liquid water to exist on a planet's surface, not too hot and not too cold. For Proxima b, it's believed there could be a narrow twilight belt, a temperate zone between the scorching day side and the frozen night side, where water might flow and potentially support life. But the reality is, we simply don't know yet. There isn't enough data to confirm whether Proxima b has water, an atmosphere, or the conditions needed for life. Only a dedicated interstellar mission could answer that question definitively, and that's where the Sunbeam concept and other proposals come in. One notable alternative is Breakthrough Starshot, a visionary project championed by Stephen Hawking and Freeman Dyson. This approach proposes sending a microchip-sized probe attached to a light sail, driven by a powerful laser array on Earth. While innovative, it takes a miniature-scale approach, sacrificing instrument payload and durability for speed and simplicity. In contrast, the Sunbeam project envisions sending a full-scale 1,000-kilogram research probe powered by a solar-stationed platform emitting a focused relativistic electron beam. It offers far more scientific capability, though it comes with greater complexity. So, when will it launch? Sadly, not anytime soon. As elegant as the Sunbeam concept sounds, it's still entirely theoretical. The technology, especially the generation and precision aiming of a relativistic electron beam over interstellar distances, doesn't yet exist. Major engineering challenges must be overcome, including developing the solar-stated platform, managing beam focus, and ensuring perfect alignment between the emitter and the traveling probe. Even the slightest misalignment in the beam's trajectory could spell disaster, causing the beam to miss the spacecraft entirely and end the mission before it truly begins. Compounding the challenge, the further the probe travels, the more energy the beam requires to remain effective. And since the solar-stated platform must operate near the Sun, it would need to be constructed from materials capable of withstanding extreme heat and radiation. But here's where the vision gets exciting. Many of the core principles behind Sunbeam propulsion already exist. For example, the Large Hadron Collider, LHC, at CERN already produces particle beams with greater energy than what the Sunbeam system would need. Modern beam guidance systems from particle accelerators could, in theory, be adapted for interstellar precision. And as shown by the Parker Solar Probe, we've already built spacecraft that can survive close proximity to the Sun. Still, not all the technology is ready. One major gap is the thermoelectric generators needed to convert the Sun's heat into usable electricity for the solar stated. These exist only as theoretical concepts. The materials, systems, and infrastructure to create such solar power plants in space don't yet exist and will take years of development. How long until launch? Even under the most optimistic scenarios, experts believe it will be at least 20 to 30 years before a Sunbeam prototype is ready for launch. That timeline depends not only on solving huge technical challenges, but also on securing long-term funding and global support.